Okay, let's get started. So the last thing we need to make this class be able to analyze pretty much any power system in the time frame that we're talking about is to come up with an equivalent circuit of our transmission lines. And remember, a transmission line is a pretty complicated engineered piece of equipment or whatever you want to call it, multiple pieces. So what we're going to try to do is come up with how that transmission line looks in terms of resistors, inductors, and capacitors so that we can analyze systems that have transmission lines. And more particularly, we're going to be interested in what's happening at each end of the transmission line. We are considering what happens in the middle of the line, perhaps, particularly under faults. But generally speaking, we only really care about the ends of the line. So we'll really focus on that. But if we had more time and if we love to do electromagnetics, we actually could spend some time showing how we come up with capacitors, inductors, and resistors for the representation of a transmission line. But we don't really need to get into that level of math to be able to understand how to do equivalent circuit modeling. So as long as we take for granted that we can have any piece of wire, and a wire, whether it's a transmission line or not, is basically a transmission medium, right? It could be for high power applications like what we're talking about for this class, or it could just be for very simple, coax cable, bringing cable TV to your house, essentially. So in any case, we're going to use a lot of the same terminology that you see for communications that we'll see here. But again, we'll spend most of the time looking at higher power applications. So here is our transmission line, and we're looking at everything from the end of the receiver. And that is important to us because they're the ones who pay for the bills. So the receiver, or the receiving end, another term that we'll use, is really what the focus is. And so we set our voltage at the receiving end. That is a fixed point that we're trying to maintain and control so that our customers are satisfied with the power that we're providing. We also have a load, right? And we're getting paid based on the load. So we know what the current is at that particular receiving end. So our starting point is at the end, not at the source, but at the end where the load is. And you can see that I've got a voltage and a current as my reference. And depending on the length of the transmission line, I will get differential voltages because I've got series elements and I've also got a parallel element. If you remember, when we talked about elements that are in series, we'd love to build them and put them in the Y bus very quickly, but that's hard to do when they're in series, right? So the first thing we do when we're working with elements that are in series is we add them together as impedances and then invert. So you see in this diagram, we have an R and a J omega L. We don't have a G and a Y term. But our capacitor, which is in parallel essentially with the line, we immediately convert that to an admittance because our Y bus calculations will be really simple if that's already converted. So we have R, J omega L in series, and then we have Y, which is our admittance for in parallel. And at the end of where we're interested in, so we're just going someplace along the line, we have some differential length, and we're going to get a voltage, our base voltage, plus the differential voltage. And similarly, we're going to have a current plus some differential current. And the differential current exists there because we have that shunt to ground. So if we're operating at 60 hertz or 377 radians per second, we see that R plus J omega L is equal to our impedance. And our Y term is G plus J omega C. But more often than not, you're not going to get any real conductance with our Y term. If you have some conductance there, it's usually if you have a bad insulator in the real world. So you've got some current that's actually leaking from the line to ground, which we would never want. We have a little bit of capacitance, but we don't want to consume any power that way. So in all cases in this class, we'll assume that G is equal to 0. In most cases, we'll assume that R is equal to 0 as well, because again, that J omega L is so high that if you include a value of R, it really doesn't mess up your results all too much. So this is our per unit length, not per unit, but per unit length equivalent circuit model. Oops, doesn't want to move forward. So now we're going to go ahead and start to derive some of our relationships. And the first thing we're going to do is we're going to see how we'll develop the differential voltage. Yes, sir.
So that's the equivalent circuit of the transmission line. So what do you mean by transmission line? Like just two cables?
Nope, it's a three-phase transmission line. So this is a single phase representation of a three-phase transmission line because all three phases are the same.
Now, three phase is only like, what do you mean? So where does the inductor and capacitor come from?
So if you think about a wire, right, it's basically a metallic element. And then you have ground and you have a potential difference between the two. So the transmission wire itself is part of the capacitor. So you have some capacitance to ground, right? You have a big insulator, but you have a plate here and a plate here with an insulator between them. So that's a capacitor. The reason why there's an inductor is as the current is flowing down the line, it's generating a magnetic field. And those magnetic fields amongst the other phases are interacting with each other. The resistance is because you have a piece of aluminum, right? So you've got some resistance associated with it that you can't make it go to zero. So here's our differential voltage calculation. It's just the current I times my impedance Z or lowercase z. And then that's that differential distance away from the receiving end of the line. And then our delta I is just going to be equal to our original voltage plus our delta V times Y. Notice this is times Y, not divide by Y, because remember, Y is admittance. It's 1 over Z. So it's effectively dividing by Z. But because we've converted to an admittance, we can multiply. And then again, that's our differential, multiply that by a differential length. Because our voltage tends to be so much higher than our differential voltage, we're going to ignore that for our differential current calculation, and we'll just use V, Y, dx. And so now we can substitute into our previous equation, our current, our DI, and we see that dV dx equals ZI dIx dx. And that's going to be equal to Y times V. So essentially what we're doing is, sorry about that. I don't know why it's, oh, let me go. There we go. So this element over here is over here. And then we're just dividing, well, we're substituting this term and we've got here. And then we just bring in our DI term, which is over, and that we substitute in for here, okay? So our dV dx is equal to ZI dIx dx, and that equals to Y times V. So now we're going to go ahead and set up a second order differential equation. And it doesn't have anything to do with the time domain. That's okay. It's based on a differential length, not a differential time. So we're just rewriting our equation, dV of x equals ZI dIx dx, which is YX. Sorry, YV. Then we're going to take the derivative of our terms, of our equation here. Now we have the second derivative of Vx, and that's going to be equal to Z times dIx. And that's going to be equal to ZY times V. So now we bring our term over, our ZYV term, and now we have a second order differential equation. We have second derivative dV minus ZYV, and that all equals 0. So for our math focus people in here, what kind of an equation that is that? Second order homogeneous differential equation. Homogeneous, I call it homogeneous. Was it homogeneous or homogeneous? I don't know. Is it homogeneous? We'll call it, I don't know, we'll just call it this equation. How's that? We'll make it easy. Okay. All right, so let's determine, come up with a term. This is a definition, but this is stolen from communication systems. Our gamma is equal to the square root of our admittance times our Z. And that has a real part and an imaginary part. So the propagation constant has two parts. It has an attenuation constant and a phase constant, right? Because it causes a phase shift in our waveform depending upon, what the actual impedance ends up looking like. So we're going to substitute that in here. And the reason why we substitute it in here is because it's a very easy Laplace equation to solve, right? Go ahead. Yes.
Instead of because of phase constant, does it mean that depending on the how close the wire are and then the distance, it creates the phase shift on the line?
It's more than that. It's like how many bundled conductors you have per phase, how close they are to ground. Like in the case of an underground cable, its capacitance value is a lot higher than an overhead cable. So it has a lot to do with the construction. There's a lot to it. There's a lot more to it than just, spacing things. It's a whole process for it.
And then just by doing that, you can create the phase shift in the line.
You can create a phase shift, but generally speaking, you want to try to keep that to the minimum you can. Yeah. Yep.
There's the possibility.
Yes. Yep. So if you remember from Laplace, and everybody here has had Laplace, probably been a minute, but you've had Laplace. Second order derivative of a function is just multiplication by s. And then no derivative of that function is just you just convert it to the Laplace domain. So our differential equation in the x domain now just becomes v of s times s squared minus gamma squared. That equals 0. We do the quadratic equation to break up our differential equation in s minus gamma times s plus gamma and set that equal to 0. So if we go back into the time domain and we have two first order circuits, so let's not say it's a underdamped system where we have a complex result. We end up with our v of x. So any point on the line, our voltage can be set equal to K1 e to the gamma x plus K2 e to the minus gamma x. Okay. And then we do a little bit of math to kind of make it a little bit more simple, although it doesn't appear like it. But we end up breaking up the term v of x equals K1 plus K2 e to the gamma x plus e to the minus gamma x over 2, and then plus K1 minus K2 e to the gamma x minus e to the minus gamma x over 2. We're going to redefine those lowercase k's just to simplify it down a little bit. And then our equation becomes K1 e to the gamma x plus e to the minus gamma x divided by 2 plus K2 e to the gamma x minus e to the minus gamma x over 2. If you remember from your trig identities, and I don't know, how many people have seen hyperbolic sines and cosines in their careers? 1, 2, 3. It's not often that you see hyperbolic sines and cosines, right? Because does anybody know what the sine is? Oh. I'm not sure why that keeps doing that. What is the sine of omega t equal to? Does anybody know what that is? Written as complex numbers.
Minus for sine of thing.
Well, let's do it. So we know e to the j omega t, right, is going to be sine of omega t, cosine of omega t, cosine of omega t plus j sine of omega t, right? That's Euler's or Euler's identity. And e to the minus j omega t is the cosine of minus omega t plus j sine of minus omega t, right? We're just substituting in theta being equal to omega t. The cosine of omega t and the cosine of minus omega t are the same, right? And the sine of omega t is equal to the sine of minus omega t is equal to the sine, negative of the sine. So cosine of omega t negative is equal to the cosine of omega t. And the sine of minus omega t is equal to minus the sine of omega t, right? So if I add, or I should say subtract e to the j omega t positive minus e to the minus j omega t, what I'm left with is 2j sine of omega t, right? Because the terms will cancel out. So sine of omega t is equal to e to the j omega t. I'm not sure why this is not writing. Minus e to the minus j omega t all over 2j. Do you all remember that? May or may not have seen that. That's how you can go from complex exponentials to sine waves pretty easily, but you can do the same thing for cosine. The problem is this here, or this here, I should say, does not look like that. It's close, but it does not look like that. Remember, gamma has a real part and an imaginary part. The j times omega t, it's purely imaginary. So those two are cosines and sines, hyperbolic, right? Not regular sines and cosines, but hyperbolic sines and cosines. So if you haven't been exposed to hyperbolic sines and cosines, and even those who have been, you probably don't remember, here's how you actually plot the hyperbolic sine and cosine. Okay, that's the actual results of plotting. And I also gave you the derivative because it might be hard to tell, but if you take the derivative of the hyperbolic cosine with respect to whatever variable, you end up with the hyperbolic sine. Okay, you can see that if I take the derivative of this side over here, I end up with this, and this side gives me that, right? Now, if I take the derivative of the hyperbolic sine, then I end up getting the hyperbolic cosine. So just like in when you do like sines and cosines, you take the derivative, you can get the other waveforms, but it's actually even simpler with hyperbolic because you don't end up with taking the derivative of sine and getting the taking the derivative of cosine and getting minus the sine. So it works slightly differently when you do it that way. The other thing too is you can actually break up your hyperbolic cosines or sines. So this is important if you need your calculator, if your calculator struggles to do taking the hyperbolic numbers, the hyperbolic complex numbers. So the hyperbolic cosine is just cosine hyperbolic of A plus just the regular cosine of beta, then plus J sine hyperbolic of alpha times sine of beta, all right? Your TIs may or may not be able to do hyperbolic sines and cosines. MATLAB can do hyperbolic sines and cosines, no problem, or our complex numbers, no problem. So that's just a trig identity. You may want to keep that in your back pocket because that's the way that you can use your calculators to make that work. So now we have this equation over here, right? K1 hyperbolic cosine of gamma x plus K2 hyperbolic sine of gamma x. I need to figure out how to solve for K1 and K2. Well, these are linear equations, and so if I can solve for any place on the line and solve for K1 and K2, then that means that that K1 and K2 that I solve for is applicable for the entire equation. So I can pick any place on the line, solve for K1 as a function of either V or I, do the same thing for K2, and now I've solved for my unknowns at this point, my K1 and K2. Let me minimize this because it's kind of chopping it off. All right, so let's start off with the first one. Let's start off right at the receiving end. When we're at the receiving end, x is equal to 0, right? If I'm at the receiving end, there is no distance. X is equal to 0. And I know that the voltage at the receiving end is VR, or V at the receiving end. And I'm going to set that equal to K1 cosine hyperbolic of 0, because gamma times 0 is 0, plus K2 sine hyperbolic of 0. Remember when I said I defined those functions for hyperbolic cosines and sines? Well, you can see over here, because if I go back over here, I can see that the hyperbolic sine of 0 is 0, and the hyperbolic cosine of 0 is 1, right? Those are actual numbers. So I can take that information and I can substitute in 0 over here and 1 over here. And what I end up with is VR equals K1. Everybody see that? By taking it at the receiving end, my hyperbolic sine term cancels out, right? Because it goes to 0. We saw that in the plot. And now all we're left with is K1 hyperbolic cosine of 0, which is 1, which allows me to solve for K1 equal VR. So I have my first constant. I've solved for K1. Now I can't, find another line representation. I can't figure out how to go back and solve for that. I don't want to, I only have one line or the end of the line. So I could go to the other end of the line, but I don't have really good information on that. So if it's possible, I'd like to use my current value, IR, or my receiving end current, to go ahead and get my values. So if I take the derivative of my equation that I solved for, the derivative of the Vx equation on the top, and I set that equal to all the way back at the beginning when I said dV is equal to IR, or IZ, right? So right here. If I take the derivative of that equation, then the advantage of taking the derivative is I now have converted hyperbolic cosine to sine and hyperbolic sine to cosine. So when I plug in x equals 0, now what I have is z times ix of 0 is equal to K1 times that stuff plus K2 gamma times the hyperbolic cosine of gamma x. X here is equal to 0, right? The reason why I didn't specify here, because I know that sine hyperbolic of 0 is 0. This goes to 1. So what I'm left with is z times I of 0 is going to be equal to the K1 goes away, and I'm left with K2 gamma, and that's it. So now I can solve for K2, and that's equal to I0 z over gamma. What is I0 equal to? That's the current at the receiving end, right? All the way at the beginning of the line. So instead of calling I of 0, I will call it IR. And now I have a way of solving for gamma. So I've got z times IR over gamma. I'm going to make one substitution to simplify the equation a little bit easier. And I know that gamma is equal to the square root of yz. If I divide z by the square root of yz, I'm going to end up with the square root of z over y. And then I multiply that by r. So my final equation is going to be VR cosine hyperbolic plus IR times ZC sine gamma times x. And that is going to be able to solve for the voltage at any point along the line, 1 foot away or at 1,000 miles away. Wherever the length of the transmission line, I can use that equation. If you remember, and everybody here says they've taken ECE351, or most of y'all have taken EMAGs. Does the term Z sub C ring a bell? It's the characteristic impedance of a line, right? So remember how if you terminate a line, a transmission line with its characteristic impedance, then what ends up happening is you don't have a ringing back of the waveform. So that square root of z over y is the same characteristic impedance that you calculated there. So we'll just use the term z sub c here as well. Okay? Yes, sir. IR is the current at the receiving end. So go all the way back to the beginning. And this is the receiving end. So all the way back here, right, where the transmission line is feeding the load, that's where the load receives power. So that's IR and VR.
And then Z and Y.
This is Z. And that's Y. Yes, sir?
Really quick, is, just to be sure, the K1, K2.
Yep.
They're the ones that kind of bring the units into the.
Correct.
Right?
Very good. So what one of your classmates noticed, if I look at my equation, and that's a really good setup for when we look at two-port parameters, you'll notice that this V is equal to something. Well, we know that this is a unitless quantity, right? The cosine of a number is just a number, right? It's not any units. So if we want to have unit consistency, we know that this has the unit of volts. So that had better have the units of volts as well, right? As does this had better have the units of volts, right? And they do because this is IR, which is a unit of amps, and Z sub C has a unit of ohms, and amps times ohms is volts, right? Remember Ohm's law? So yes, those two, it's important for us to give us our units so that we can jive, so that we actually get a volt equals a volt.
What is it, ohm squared, where's the ohm squared? Z ohm, Y is 1 over ohm.
Yes, yeah. So if you go all the way back, yeah. But yes, that's right. But those are per unit length too. There's even the little z and the little y is actually ohms per unit length. And y is that, but when you invert them, they still cancel the unit lengths out. Yep. So you can do the same thing for I. Same process where you have IR hyperbolic cosine and VR over ZC hyperbolic sine. So we just solve for K1 and K2 for not only our voltage differential equation, right? We have a solution for the V of X, but we also have a solution for IX. We've got two solutions. They work out beautifully.
So this formula give us for the V of X, so it give us the voltage at a certain distance.
At any distance.
Any distance.
That's what the X is. You can pick any distance you want, and it's going to go ahead and calculate what the voltage will be, that V of X equation. So if you want to be halfway down the line, you plug in whatever half the distance equals. And as long as you've got gamma and Z sub C, and you know what the nominal voltage and load is, right? Because you've got to have some way of saying, hey, it's a nominal 138 kV line, and the load is 500 megawatts. I mean, you can't predict what the voltage is going to be if you don't have those two. Then you can solve for it at any point on the line. Okay. And then the last equation here, right? We talked about that on Tuesday. That was our exam review. All right, we'll go over where we had efficiency as P out over P in, because we are going to be talking about transmission line efficiency here. All right, let's take a look at a simple example. We have a 765 kV transmission line with a nominal 765 kV line-to-line voltage at the receiving end. Remember, the customer is expecting you to provide 765. The load connected at the receiving end is fairly big, right? 2 gigawatts plus 1 giga VA. A pretty big power demands, right? But this line is operating at 765 kV, so you're not going to be moving 50 watts through a line like that. You're going to be moving big power. We have our little z is that value there in ohms per mile. Remember how I said it's the ohms per unit length. We also have our admittance, which is in mhos per mile, not in Siemens, but in mhos, because we have our J term, right? So the mho symbol inverted, I mean, the ohm symbol inverted is the mho symbol. That's why it's upside down like that. Now we're going to go ahead and calculate what our propagation constant is. So we plug that in and we get the value as shown. You can read the numbers better than I can say them. And our characteristic impedance is about 263 ohms, which is pretty common, right? Not too crazy of a number. Now to analyze a transmission system, we always have to go and represent it with a single phase representation of our system. We can't use 765 kV because that's across two lines. We must use a phase to neutral voltage. So we're going to take our 765 and divide that by a square root of 3. And then that becomes our reference. We're going to set that equal or have an angle of 0. So our receiving end voltage, nominal phase voltage, is about 442 at an angle of 0 kV. Now we got to calculate what the current is, right? So we have load, and we got to figure out what the current is. So S equals VI conjugate for single phase. For three phase, it's S equals 3 times VI conjugate. And this 765 kV line is pulling just under 1700 amps current. So just under 1700 at an angle of negative 26.6. So then I plug those into my equations, and I've got my voltage equation written as a hyperbolic with my IR and my Z sub C. And I actually can plot what the power or what that line looks like for any distance. This is a long transmission line. This is 1,000. Well, I'm assuming if we can go up to 1,000 miles in length, which there's no transmission line that I am aware of that's anywhere close to that. But it's a little hard to tell. Let me move this out of the way just a wee bit. Oh, where's my mouse? Sorry, my mouse won't show up. So, all right. So the blue line is the amount of power that is consumed in the line. So the further away you are from the receiving end, the more power you need to put into it. And if you look at the left axis, your left, you'll see that to put in the 2,000 megawatts right at the receiving end, you can see that there's about 2,000 megawatts, right? That intersects that. If you go all the way to the beginning of the line, I have to put in more than 2,000 megawatts because that line is consuming power. Remember, there's a real part associated with the line. So it might be consuming 200 megawatts of real power that's just being wasted as heat. The red line is the reactive power. And this is what gets interesting. So at first, it starts to be a tremendous amount of power. So the 1,000 MVA is all being provided by the system. But as I go further and further along the line, further away from the end of the line, you can see it starts to drop until it gets almost to a minus, what is that, 1,100? And that's because this line, its admittance value, the Y value, is high enough to contradict the impedance of the line. So this line is actually supporting the system by providing reactive power. That's why it drops. Until the line gets so great, now you're talking about phase shifts, and now you actually have to start putting in, you start to get less power out of the line than before. Yes, sir. It's a capacitor. Remember, it's all borrowed power, right? So when the inductors are demanding power, remember Eli the ice? The capacitors can dump out the power. So they're storing power in part of the cycle. The inductors are demanding it. And so they'll dump power out to support the needs for the inductors. And then the other part of the cycle, they switch. So they will share power back and forth to support the needs that they have over the cycle. Absolutely. Well, a capacitor on average does not take out reactive power. It actually supplies reactive power, and then somebody needs to grab it and consume it elsewhere. So yes, capacitors are put all over the system to boost voltage, and how they do that is they increase the amount of reactive power. Yep, so they will inject bars into the system. And it works really well. You'll see capacitors, like even on distribution circuits, you'll see they look like little, I don't know, like a bread box, like three. If it's three, that they're always rectangular, or I think they're always, I've never seen them circular, but they're always rectangular, and you'll see a bunch of them on a line. And yeah, that's where you have capacitors there out on the distribution circuit. They're cheap and easy to install, and you can put a small fuse on them for protection. It works really well. The other thing that's interesting, this is getting really crazy. So now at the receiving end, you can see I started out at 441,000 volts phase voltage. But look, as I get longer and longer in the line, look what happens to the voltage along the line. It gets to almost 950 kV because of that reactive power injection. Really, really high voltages. And then it starts to drop until it actually gets to even less than the value. And you can even see that that voltage drops by quite a bit. So you started out at 765, and then you finished at less than 600. Okay? So that's how you can look at it over the line. We're not going to look at it in this case. This is just to show you what happens over the distance of a line. We're actually going to look at it at both ends, but this is what I wanted to show you. If you can look at any point in the line, this is what's happening in terms of voltages and currents and powers on a steady state. Yes, sir.
So the voltage that's coming on the other end of the line is 755, right?
It's no, at the receiving end, you have to provide it 765.
But then
At the sending end, is
Yes.
another term.
Yes.
It'll be however far away you are from the end of the line.
Okay, so now from this side at zero is like how much is that? How many voltage is that?
So at zero, that's 765.
55.
So if you're right at the end of the line, you'd only have to inject 765.
And then now at 1,000, how much we at?
You have to go less. You have to be less than 650 kV. Because look at the green line where it intersects the right-hand y-axis.
600. Oh no, 640.
Yeah, I say 645, something like that. Yeah.
But then around 400, it's all the way up there.
Yeah.
But then that's like a waste of voltage. So you use it something.
But you're not wasting voltage, right? You just can't do anything with it because you're not tapping off. And it's definitely not a waste, because if you've got 765 is what the customer expects, you're not going to connect a 950,000 volt connection point to that. So the line can handle it as long as the insulators are set up for it, everything like that. It's no problem for the line to have these voltages, but the customers don't want you to have that high of a voltage.
Which means when you make a line, you have to encounter that there might be a rise in voltage for this.
Yeah,
line, so that
absolutely. Yep.
They can hold it.
Yep.
Then now, since there's a drop of voltage at for the customers, that's bad, right?
There's not at the customer. Remember, at zero,
That's bad.
the customer is zero. This is at the generator. This is the utility is responsible for making sure their system can provide 765 kV. You, as the utility owner, have to jump through hoops. Otherwise, your customer's gonna say, I'm not connecting to you. I'm gonna disconnect, and I'm not paying you anything. So it behooves them to go ahead and set the system up so that it can support whatever needs you have.
That's right. Which means when you are supplying the voltage, and then you want the customer to receive the 755, you have to calculate how much voltage you need to put in, so that can.
Yes, that's exactly right. But again, this is, just kind of an exercise in academia. There's no such thing as a 1,000-mile long line. Like in Maine, the longest line we have is like 58 miles, I think. And I know they get a little longer in the Midwest, but once you go to like 300-400 miles in length, you would go to DC. And then this doesn't apply because you don't have reactive power in DC, right? It doesn't exist. Why? Because omega is equal to 0, right? So 2 pi FL is equal to 0. You only have resistance. So one of the things we do to size transmission lines is we use the concept of a lossless line, which there is no such thing, but it makes things easy for us. So we're going to go ahead and define something called the surge impedance. And the surge impedance is going to be equal to the characteristic impedance for a lossless line, which means R is going to be equal to 0. And if you terminate a lossless line at its characteristic impedance, you can end up with a very simple equation. Our VR cosine hyperbolic gamma x plus VR sine gamma x. And then we do the same thing for I. And then what we end up doing is everywhere along the entire length of the line, your V divided by I is Z sub C. So for those of you who are taking EMAGs, right, if you terminate a line, like if a coax cable going into your house, you're going to terminate it with a 300 ohm or 75 ohm terminating resistor. If you terminate it with that impedance, then you end up, your line looks at 300 the entire length. So you can transmit TV signals, you don't have any issues. So our transmission, our surge impedance is going to go ahead and allow us to calculate this SIL, which is called the surge impedance load. And you determine that by taking the magnitude of V and dividing by C. So Barzilay had a question, would you ever divide V by Z? Yes, if I'm just trying to get an impedance, a magnitude for S. But this only applies when I looking at a lossless line. So if my power is greater than the SIL, so the power I'm moving to the receiving end, if it's greater than the surge impedance loading, then my line is going to consume reactive power. So that means I've got to dump in reactive power into the system. If it's less than my surge impedance loading, then the current going through the line is small enough that the I squared X that the line consumes does not overcome the V squared over the V squared times Y that we would get because of the capacitance of the line. Because you get two parts, right? You get the capacitor and the inductor, and both of those are operating in different parameters. Y, the capacitor is helping support the line, and the X is helping to decrease it. So they work in tandem. So if I have very little current going through the line, the I squared X of the line is pretty small. But the voltage is always fixed at around nominal, so that V squared over that equivalent capacitance gives me a lot of reactive power. And this happens all the time in the real world. At night, very lately loaded, you get crazy high voltages on your system unless the system operators go ahead and back the system off. And that's because there's so little current on the line, but the voltages are around nominal, that you've got a lot of reactive power support at night. Yes, sir.
What do you mean by lossless? You think that there's no losses on the line?
Yeah, you're just assuming that it's R is equal to 0. So it simplifies our equations to go ahead and calculate or to design transmission lines.
But then in the previous equation, V sub C is L over C. There's no R.
Correct. That's why it's lossless. Right? The little z just becomes J omega L. There's no R term, correct? And again, this is not a precise, but it's close enough to give us some easy-ish calculations. So when you design a transmission line, there's three things you have to consider: thermal limits, voltage limits, and stability limits. And it has to do with the length of the line. If you have a short line, relatively short line, the most limiting factor is the thermal limits, the I squared R. Now, does that mean before the wire heats up, do you think, when you think of thermal limits?
Yeah,
That's what I think of. Or it changes, it's called annealing. Like for those who are into chemical processes, if you run metal at higher temperatures, it starts to anneal. But over here, it's different. When you look at a transmission line, right, you got two towers with insulators and you get sag in the line. The way that you design the transmission system is as the line heats up, it gets more sag, right? If it's higher temperatures, you get a spreading of the material. And then as you heat it up I squared R, you actually get higher levels of sag at higher temperatures. So the thermal limits are not going to burn the cable up. It's actually that your sag is going to reach below where it's considered safe. So too much sag means somebody driving a trailer under a transmission line, they get electrocuted because the sag is really low. And the thing about transmission lines, they're obviously the wire is put between two towers, but the wire is locked at those two tower positions. Any idea why? Because over time, heating and expanding, right? The wire moves a little bit and the sag would start here and then eventually it would be on the ground over time, right? So the way that they actually install the transmission lines, they pull the conductor through, they tension it, and then they bolt it on in position on the towers. And they have to make sure that it's tensioned to a certain amount so that the sag will be maintained above a certain value. So there's a lot going into it. So short lines, you're worried about too much sag. For medium length lines, if the voltage drop across the line is too high, there's only so many things the generator owners can realistically do to make sure that their customers are getting the nominal voltage. At some point, they can't do anything. Usually it's plus or minus 10% is kind of the maximum they can do. In some cases, they can do a little more, but generally it's plus or minus 10%. And then if you have a long line, that has to do with if you have a fault, one line, the system at one end of the line can start to spin a little faster than the other. And then when the fault clears, they start fighting each other. And you can actually get a system that will trip because it's not stable. We probably won't get into that too much this semester. So the surge impedance loading is the same as Z sub C for the line. You can get IR, and you can see that our VS is equal to that parameter there. You just factor out VR. So why do I do all this stuff? Well, now I can tell you approximately how much power I can move through a line. So in Maine, the maximum that we have is 345 kV. And a nominal surge impedance loading was going to result in about 430 megawatts. And depending on the length of the line, there's a multiplier in that surge impedance loading, which tells you about how much power it can move. So in general, a 345 can do about 3 times its surge impedance loading, which means you can get about 1,300 megawatts before you can't run the line any higher. Okay? Because beyond that, you're going to actually start having some issues. 765, we can run 6,000 megawatts. Much, much, much higher power values because the voltage is there. Okay? But there's a downside to that too, right? Because that 765 kV line, if it's moving 6,000 megawatts of power, you have to design a system so that any worst case scenario can happen. Any piece of equipment can be taken out of service and the system should survive. I had better have a system that's robust enough to be able to take out 5,000 megawatts just like that and still survive. In New England, we only have systems, well, the DC line comes in and that can pull about 2,000 megawatts, but all the other AC systems, 1,200 megawatts max. So the system is a little bit easier to work around those contingencies where it has a failure or a fault. And here's the multipliers. So short lines, anything less than about 60 miles, you can go a multiple of 3. That's in Maine, right? So we're pushing 1,300 megawatts. If you get more than 300, which is about 180 to 200 miles, then you've got a voltage drop limitation. That's a 5% voltage drop. If you're going long lines, so greater than 200 miles, now you're talking those lines can only run at about 1 to 1.5 times. Otherwise, you can't do it. So it's not like you can just keep bumping up the voltage and keep getting, the multiple or the corresponding multiple for power. You are limited. So you can see there's some advantages to sticking around with a system that operates at 345 within reason. New York is starting to go with higher and higher voltages. They have short lines, but in New York, they have such power demands, particularly going into New York City, that, it can't really work with the conductors that they have at 365. So they're upgrading a lot of their system. They got a bunch of 230. They're moving to a lot of 345 there. So those are very expensive projects, multi-billion-dollar projects to make those work in New York. But that's also because New York ISO, I think, is when we looked this early in the semester, the load was like 20 gigawatts, 30 gigawatts. I can't remember. Well, we can look here. You can see what the system load is right now. If I had to guess, we'll take a look, but I had to guess, I'd say 15 to 18 gigawatts is what New England is. But New York ISO is usually 2 to 3 times that. So let's see, what are they pulling? So right now it looks like they're pulling about 100 megawatts. And the real-time load in New York, oh, that's only 13,500 megawatts. It's pretty low. If I go to ISO New England and look at their dashboard, we're pulling about 8,000. And they were pulling 13, so they're not quite twice. But again, you can also see solar, right? It's a nice sunny day out, so look how little the load is at noon, right? It peaks here, well, it's gonna peak at night, it's gonna peak at almost 14,000, but there's so much solar going on right now. Almost half of the demand in ISO, in New England territory is gobbled up by the solar resources. Yeah, 7,884 versus the 13,000 whatever, so almost double what New York is. New York is almost double what we have. So they got, different set of issues there. All right, that was my last slide. Any questions? You don't have to be pros at doing, don't have to be pros at doing hyperbolic sines and cosines. We won't do that much, but it is important because we're going to be making some simplifications for with the hyperbolic sines and cosines so that we won't have to do as much legwork. Some questions? Nothing? Yes, sir.
Yes, I guess I might have kind of missed it, but, surge impedance load, like, what does that mean exactly?
That just tells you it's a power. So if your real power demand is greater than your surge impedance load, then the line is consuming bars. If it's less than the surge impedance load, then your line is supplying bars. So it's like a good sort of a basic design parameter to figure out, is this going to consume or is it going to supply?
Okay.
Yep. Okay, nothing else? Have a great day and weekend, and I will see you all on Monday. Take care, everyone.